Hello, it's me again. All right, so we're going to continue learning about hydrolysis. So we talked about anions, and now we're talking about cations. Okay, so for the cation, it's either going to be conjugate acid of a weak base. We talked about those examples, and those are going to make the solution acidic, or it's going to be a metal. And metals are pretty darn common cations. So that's the last thing we're going to talk about. So how can a metal have or cause a solution to be acidic or basic? Huh. I mean, like, how can a metal donate an H plus? That's kind of weird. So we're going to have to talk about this. The first step is that whether it's a cation or an anion, if you put an ion in water, it's going to get hydrated, which just means that it's going to get surrounded by a certain number of water molecules. That's how things dissolve. Okay, we're going to specifically focus on how metals do this. Okay, so let's take a look at an aluminum plus 3 ion. So if I throw an aluminum plus 3 ion in water, it's basically, if you look at the charge, plus 3, you're going to put double that many water molecules around the atom center. Okay, so hydrated aluminum plus 3 has these 6 waters surrounding it. Okay, this is a drawing of what it would look like. So the aluminum is here in the center, and then these 6 water molecules are surrounding it. Okay, so if you took like a copper 2 plus metal, well, then it's going to have 4 water molecules around the atom center. Okay, so hydrated copper ions look like this. So it's got the water, 4 of them, 2 plus overall, because the water doesn't have any charge, so the copper still has its 2 plus charge. All right, so that's how metal ions get hydrated. So that's totally fine. All metals do this. But sometimes the hydrated metal ion can further undergo hydrolysis. So here's where things get interesting. Okay, so if we take that hydrated aluminum ion and put it with water, this is what can happen. I'm going to show you guys with the drawing first. So you got this aluminum plus 3, and here's one of the 6 water molecules. Now you guys know water the O has a partial negative charge. So of course aluminum plus 3 is going to attract that partial negative on the O. Okay, well, here's the great part. That aluminum with a plus 3 charge does such a good job attracting that partial negative O that it actually draws the oxygen to the plus 3 and kind of distracts the O. And as a result, this OH bond weakens. Okay, so when the O gets attracted to the plus 3, this bond weakens and this OH pops off. Okay, so what this ends up looking like is you still got your aluminum plus 3. Here's what's left of the water molecule. The electrons in that bond end up sticking to the O. Those are the other lone pairs that O always has. And whoop, that H plus has escaped. The bond was weakened and the H plus was able to fall off. Well, that's how a metal can donate H plus and make a solution acidic. Okay, so that's sort of a picture of what's going on. But if I said I want you to write a reaction to show how aluminum 3 plus undergoes hydrolysis, this is exactly what I'd want you to do. So start with your hydrated aluminum plus 3 ion, okay, and we're going to react it with water. That's what hydrolysis is. We're only going to show one water molecule undergoing hydrolysis, although this could happen to a greater extent, okay? So since we're only showing one water molecule, 5 water molecules are going to stay exactly the same. They didn't change at all. But one of the water molecules is going to lose that H, and it's become OH minus, okay? And then that H plus escapes, but this H2O picks it up, and that's how you make the hydronium ion, okay? Now we're going to go back here. We're not quite done with this guy. Aluminum has a plus 3 charge. The water doesn't contribute any charge, but this guy is an OH minus because it gained that electron pair. So you got a plus 3 and a minus. This whole thing has a plus 2 charge, and it's called a complex ion. Imagine that, okay? So that's what would be produced. Now, you might be saying to yourself, oh yeah, look, I see that OH minus, like that's basic. Not the case. When that OH minus is stuck in this complex ion, it does not have basic properties, okay? So just that OH is truly just sort of along for the ride. Okay, what you need to focus on is this was produced, hydronium ions. So this solution will be acidic, okay? Whew, that was kind of complicated. So we're going to have to try that one more time. So let's just say we took some zinc chloride, the salt, okay, and we threw it in water. Now, of course, it's going to dissolve, and since it's an ionic compound, it's going to dissociate. So when it dissociates, it's going to break into zinc 2 plus ions and Cl minus ions. So you want to look at each ion individually. and I say, well, let's see, Cl minus, it's a conjugate base, yeah, of a strong acid. Okay, and that Cl minus has no desire to grab an H from water, so no hydrolysis will take place here. So this part of the salt is neutral. Okay, but the zinc 2 plus, okay, that's where we're going to see some kind of hydrolysis. So to show that, remember it's 2 steps. You have to show the metal ion get hydrated first. So 2 plus charge, so that's going to be 4 waters. So that's going to look like this. Whoops. And then it's going to undergo hydrolysis. So since that +2 charge can attract that O pretty tightly, then that OH and water, that bond is going to weaken, H pops off. So as a result, 3 water molecules stay exactly the same, but 1 water molecule loses its H plus, and you're left with OH. Okay, that H plus escapes and hooks up with this water, and that's how you make the hydronium ion. And then go back, we got to fix the charge here. Zinc is a +2, no contribution to the charge. This is an OH minus. Put the whole thing in brackets. This whole rascally thing has a +1 charge. Okay, there you go. See, easy peasy lemon squeezy, acidic solution. Okay, all right, and you guys will see, we'll soon be able to calculate the pH, and we'll have a Ka value. It's going to be a good old time. Okay, now last thought about metals. All metals can be hydrated, but not all metals can undergo hydrolysis. And you know what? It's pretty simple. It's all about this charge. You have to have a pretty big charge to be able to attract that O strongly enough so that this bond does get weakened and that H can pop off. Okay? So to summarize that. So not all metals hydrolyze. You know what? If you got this like lame +1 charge and it's big. So some of it's about charge density. How much charge is spread over an atom's space, okay? So if you got a +1 charge, it is not going to have enough pull on that O to cause hydrolysis to occur. Or even a +2 charge is better, but if it's kind of a big atom, that +2 charge is spread over a lot of space, nope, not going to be strong enough to cause hydrolysis to happen. So of course, some great examples, alkali metals. Okay, so like Na+, K+, Li+, etc. You know what? Just not going to be able to pull on that O in a water molecule strongly enough so that that OH bond just doesn't get weakened and that H doesn't pop off. It has no effect on the pH. And then I said big +2 charge metal. So if you look at the second family on the periodic table, but near the bottom, you know, like barium 2+, strontium 2+, nope, not going to undergo hydrolysis. Yeah, and that's good. So that's a pretty good list. Now, if you're a small +2 charge metal, or for sure +3 or higher, you will have enough pull on that oxygen in the water molecule so that that OH bond does get weakened and the H plus will pop off. So aluminum is sort of the classic example. Iron +3, pretty darn acidic. And then like copper 2+, not going to hydrolyze as well because it's only got a +2 charge, but copper is pretty small. As you go across the periodic table, atom size decreases. Copper is pretty far to the right. Zinc 2+ is another good example. And last but not least, Holy Toledo. If you can throw in something like zirconium, not zinc, sorry, zirconium +4, whoo, really going to hydrolyze well and make a pretty acidic solution. Okay? All right, so to summarize, the cation is either going to make the solution acidic. If it's a conjugate base, incorrect, conjugate acid of a weak base, which is really easy to identify because it's not a metal. So if the cation is not a metal, it's probably a conjugate acid of a weak base, and it will make the solution acidic. And highly charged small metals. Or the cation will have no effect, it'll be neutral if it's a small charged big metal. Okay? Whew, I think that's the end. So what I want you guys to do is review these notes, come in with questions, but I do want you guys to do these examples. And I think the video is going to cut off any second, but I'll try to do an example. What you want to do is basically split it into ions. I'm going to start with this one. Like, where's the cation? Where's the anion? I start with the anion because I actually recognize ClO4-. So if that's my anion, the whole rest of this thing has to be my cation. So you see how we did that? So start with the